So far with integration, we have worked with some of the basics. We've worked with our E's and our LNs, and then we even worked with U substitution the last chapter in order to work through undoing the chain rule. There are certain problems that you will encounter that all of these methods are not going to help you to find, and so in section 5, we need to pick up some additional integration techniques. Integration by parts, it is an integration method which enables us to find antiderivatives of some new functions, such as undoing our ln x, which we have yet to do, as well as an antiderivative of products of functions such as x squared times ln x and x times e to the x. So if the function we're trying to integrate can be written as a product of two functions, we'll call them maybe u and dv, then integration by parts lets us trade out a complicated integral for hopefully a simpler one. So here's our integration by parts formula. It isn't going to involve our u substitution. So we say the integral of u dv is equal to uv minus the integral of v du. And then for definite integrals, we would just throw in the a's and b's. So here's going to be the part that you want to do, or the best advice for working something like this. We want to make sure that we're picking our u correctly, and then we're going to pick our dv correctly, and we're going to be able to separate this. And so I think the best way to help you with this is to kind of work through some examples and give you some tips and tricks along the way. And so in the function, how do you know how to use integration by parts, or that you should use integration by parts? It's when you have a product of two things and your simple u substitution will not work. If I were to make u equal to x, the exponent on the e, it would not compensate for the x that's out front. So really it's going to be a product of functions that your simple u substitution doesn't work out. Now, how do I pick what things are going to be? Well, typically you want to pick your u and dv. So we're going to pick that from the product. What do I want to pick to be u? I want to pick the function that when I take the derivative of it, it reduces. And so I'm going to pick x to be that u. What do I pick to be dv? The rest of the function, e to the x dx. Now this can be a little bit tricky because you are going to have to switch your mindset from derivatives and integrations all within the same problem. What we're going to do next, just like what we did with u substitution, I'm going to kind of make this problem go away. I'm just going to focus on what I have here. For u, I'm going to find a du, meaning I'm going to take the derivative, and the derivative of x is just 1 dx. Don't lose any of these dx's along the way. dv signifies that I want to integrate, so I'm going to take that backwards and go, what is the integral of e to the x dx? And that is e to the x. Once you create your table over here, then go back to your problem and we're going to work through it. So I'm going to pull my formula down. u dv is equal to uv minus the integral of v du. And we're going to start plugging in. So u dv, this is what our original problem was. X e to the x dx. Then using my substitutions over here, I'm going to plug into my formula. So u is equal to x, v is equal to e to the x, minus the integral of v, which is e to the x, du, which is dx. What that does is that already pulls out a term for you, and so the only part that we have left to do is to integrate this part, and we can simply integrate that because the integral of e to the x is just e to the x plus c. And then now we have our function integrated. So integration by parts is going to be very handy for you, but again, it's going to be based off properly choosing your u and dv. So let me give you some tips and tricks to help you with that. Here's our rule of thumb. When you're selecting the u for by parts, select a logarithmic expression if one is present. If not, select an algebraic expression like x or dx. So when selecting the u for parts, select the logarithmic expression if present. If not, select the algebraic expression. Or again, I like to pick u to be the part that as I take the derivative of it, that it would reduce. This one, we're going to have to go into this part of selecting the logarithmic if it has one. So you can see we have a definite integral, so we're going to have that added step of plugging in the 1 and 4. But first thing we're going to do is integration by parts. I'm going to pick u and dv. U we are going to pick as ln x. dv is going to be everything else that's left over. Now, another way to remember that you're going to pick the ln x for your u is if you had come in here and said, oh, let me pick 6x squared dx and let me pick ln to be dv. I have no way of integrating ln x and figuring out what v could be. So that would be the point that you go, oh, that didn't work out. Let me switch it back and see if that works. Once you pick your u, you're going to take the derivative of it, which we know that to be 1 over x dx. Then dv, you're going to integrate to get v. So I'm going to add 1 to the exponent. That gives me a 3. Divide by the new exponent. I'm going to go ahead and reduce that, and that gives me 2x cubed. Then I'm going to write my formula. The integral of u dv is equal to uv minus the integral of v du. Now, when I write out my u's and v's, always make sure my v is a pointed, very much pointed at the bottom with my handwriting, and my u has the stem coming off of it so I can correctly distinguish what is what. So this is going to be equal to u, which is ln x, times v, which is 2x cubed, minus the integral of 2x cubed du, which is 1 over x dx. So let's clean this up in the next step. I typically like to put whatever I'm multiplying by ln x out front so it doesn't actually get combined with that x, because I am taking the ln of that x and multiplying that number times 2x cubed. Minus x cubed divided by x reduces to give me 2x squared dx, and then we can integrate it. 2x cubed ln x minus add 1 to the exponent, divide by the new exponent plus c, and then just write this as neatly as we can. We also need to remember that this absolute value of x's, I forgot along the way, minus 2/3 x cubed plus c. And so there would be my function. So you can see this integration by parts worked really nicely. Now the last part is we do have to evaluate with 4 and 1. So let me just come over here to the side. I am evaluating this, so I don't need the plus c, from 4 to 1. So just use your calculator to help you. 2 times 4 cubed, ln absolute value of 4, minus 2/3 4 cubed, minus, plug in 1. So let's see, 2, that'd be 2 ln 2 minus 2/3 times 2 cubed. I would use the calculator on the screen as you work through that, and that ends up giving you a value of approximately 132.446. And so again, the evaluating can be a little tricky just because of the functions you're working with, but the main part I'm trying to show you here is just your integrations with that integration by parts. It just takes practice, so hopefully the homework will help you with that, or reach out to me, I'll be of assistance. Now, another way of integration is using tables of integrals, and there's many techniques of integration we will not be studying. Many of them lead to very general formulas that can be combined into a table of integrals, and so kind of a cheat sheet for working with your integration. I know you like that word that I just used there. Anything that we need to reference will be given in the instructions of your exam. You will not need to provide that on your own. But this table of integral examples is really nice because it shows us a way of taking these two integrals here, and then through practice and generalization, we're able to get what those integrals are. And by no means would I ever want you to have to memorize that. But I do want you to be able to output those. The variable that's being squared is your x represented here. The constant that's being squared, you may have to square root, and that would come in here with your a's, and likewise with the second one. And again, thank goodness for someone else working through the general sense, because I would much rather plug in with x's and a's than have to work out all the pieces of that got us to that point. And so let's work an example here. This is one, and it says integrate 5 over x squared minus 9 dx. And how do I know that I even want to use my tables for this one? Well, it's because if you were to pick your denominator to be u, going back to your simple substitution, that would be x squared minus 9. So du would be equal to 2x dx. And you can see we have no other variable going on over here in this problem. So we would have to have someone else or something else to help us with that. So this one looks really similar to that first integral in our table that we had. And it said that if we have the integral of 1 over x squared minus a squared, we would have our answer. So let's evaluate what these pieces are. First of all, this 5 is just going to go along and come out front, so that I'm just working with 5, the integral of 1 over x squared minus 9. So you can see I now have a 1 on top, I have my x squared here, and then 9 is going to be equal to my a squared, so a would just be 3. From our table, it said that this would be equal to, let's put this here, 1 over 2a ln of, let's scoot over a little bit, x minus a over x plus a plus c. And so let's apply that over here. So this would be equal to 5, which was already out here, 1 over 2 times a, which we determined to be 3, ln of x minus 3 over x plus 3 plus c. Clean that up. That gives me 5 over 6 ln of this rational function here. And so you can see that went really easily, much more than the proof of how that table came to be. Now I want to go ahead and do a couple more examples so you can realize how these pieces work out with the table of integrals. In this next one, it got a little bit more complicated. It's got an x squared in the top and an x to the 6. So let's see what we can look at with this one. Let's first look at that x to the 6 and see if we can figure out how that can become a squared. This x to the 6, think about this, that this would also be considered like x cubed squared, because when you have power to power like this, you multiply. So if I was looking at this function, this would be like x cubed squared plus, I know 4 squared is the same thing as 16, and then x squared. Now I have it set up in such a way that I could work with the pieces and figure out how I could sub these back in. So let's go back to that natural log function and let's see what we can do with it. I'm going to use my u substitution this time. Let's let u be equal to x cubed. And this was a dx here. And so du would be equal to 3x squared dx, and I have that x squared dx, so I'm going to divide by 3 on both sides. So I get 1/3 du is equal to x squared dx. So subbing into my problem, I now have u squared plus 4 squared, 1/3 out front, du. And so doing that blue substitution related it back to what I was doing with my natural logs. And so I'm going to say, okay, well then that would be 1/3 from the problem. And then looking at the previous table, going all the way up here, let me show you what I'm looking at. We're working with this one now because I have a plus sign underneath that square root. So you can see I'm not going to have a coefficient like I did in the previous one, and I'm going to have this solution. Just want to kind of reference that for you. And so this would be equal to 1/3 ln of u plus the square root of u squared plus 16 plus c, just doing that substitution, and then change it back into your x's. So 1/3 ln of x cubed plus the square root of x to the 6 plus 16 plus c. So you can see that although the tables give you an answer, you still have to know u substitution to make it look like the table and still be able to work through that. So we can't just get to the point where we go, oh, it already has the answer using that table, I'll just kind of plug in and go. You still need some technique to get you there correctly. So let's look at some more exercises, and these are just exercises at the end of the textbook, and so I'm just going to kind of grab some and work through them. It says a function u or dv is given, so they're giving you a starting point. Find the piece u or dv which is not given, calculate du, and apply the integration by parts formula. So they're really kind of helping you through this. So let's use our highlighter to help us with this. If u is equal to ln x, then that means we need the remaining part to be our dv. Now I am going to go ahead and put that 12 out front so we don't really have to deal with it right now. So this is going to be 12, the integration of x ln x dx. So if u is ln x, then dv is x dx. When we come over here, we're going to find du by doing derivative, so that would be 1 over x dx. And we are going to integrate dv, so take it backwards. So I'm going to add 1 to the exponent. That gives us, let's see, v would be equal to add it to the exponent would be x squared divided by 2. So again, you got to be in the mindset of one part's being derivative, one part's being integrated. Now our formula is uv minus the integral of v du. So I'm going to say 12. Let's see, uv, so I'm using u and v, so it would be 1/2 x squared ln x minus the integral of v, which was 1/2 x squared du x dx. And then I'm going to work through this. So let me go ahead and distribute this 12 back in here. So it gives me 6x squared ln x minus 6 integral of x squared times x would just be x cubed dx. And then that I can integrate just by adding 1 to the exponent and dividing by the new exponent. So it would be minus 6. Let's see, add 1 to the exponent, divide by the new exponent plus c. And then clean that up once more. 6x squared ln x minus 3 over 2 x to the 4th plus c. And so pretty handy that they're kind of giving you that jumping off point. But you either want to pick your ln x to be u. If there is no ln x, then pick the part that would decrease down when you take the derivative. So let's do the next one. They give us a little bit different part. They give us the dv. And they say let dv be x to the 4th dx. So that means u is going to be ln x, but that's kind of our trick to pick your ln part to be u. So u would be equal to ln x, and then you want to integrate and derivative. So integrate dv, that gives me v to be 1/5, oh, don't need that d, v to the 5th, add 1 to the exponent, divide by the new exponent, and take the derivative of ln x, and that's 1 over x dx. And so again, we're using our uv minus the integral of v du. So u would be ln x, v would be 1/5 v to the 5th. And I always put this part in front of my ln x again so it doesn't accidentally coincide with this x. Why am I doing v? That's an x. Minus the integral of v, which was 1/5 x to the 5th, du, which was 1 over x dx. So cleaning that up, that gives me 1/5 x to the 5th ln x minus 1/5 the integral of x to the 5th times 1 over x just reduces u to x to the 4th dx, and then we can integrate that. So 1/5 x to the 5th ln x minus 1/5 x to the 5th over 5 plus c, and then I can combine those two together. And then I'm just going to use an eraser, and that would give me 1 over 25 x to the 5th. So you can see they kind of follow suit. Hopefully this practice is helping you out. Now if we look at evaluating integrals, it's still going to be uv minus v du. So practice with that, and then when you get to this part, once we finally get to these conclusions, you can plug in 1 and 0, and I don't doubt you're evaluating. But if you need additional help, reach out. I'll be happy to help. And then you're also going to see problems such as these two, where these are going to be using those formulas from the table. So I would absolutely have those yellow boxes, formulas from the table, or that uv minus v du to kind of help you with it. But I wanted to look at some sample exercises and show you how these would work out and the possibilities of homework questions you're going to face. If you need any additional assistance, please reach out to me. I'll be happy to help.